Hello and welcome to the lecture 4 of this lecture series on complex number. Now we are going to learn some application of De Moivre's theorem. First of all, we are going to see the nth root of unity. That means the nth root of the complex number z is equal to 1. Z is equal to 1 is a complex number that can be written as 1 plus I 0. So from here we can find the modulus of z, which is equal to under root of 1 square plus 0 square, which is equal to 1. So the modulus of z is equal to 1. And similarly we can find the argument of z. Z is equal to 1 can be written as cos 0 plus I sin 0. Cos 0 is 1 and sin 0 is 0. So we will get ultimately the z is equal to 1. So here the argument of z is equal to 0 degree. So arc z is equal to 0. The nth root of the complex number z is equal to 1 is called the nth root of unity. Now the complex number z is equal to 1 can be written as cos 0 plus I sin 0 can be written as cos 2k pi plus 0 plus I sin 2k pi plus 0, because this angle 0 can be written as the multiple of 2 pi. So here k is an integer. Now by the theorem, if z be a non-zero complex number, m be a positive integer, then there are m distinct value of z to the power 1 by m. That means there will be m distinct values of mth root of z. So we can apply the same thing for z is equal to 1 also. So z is equal to 1. I'm taking the power both side here, the power 1 by n. So z to the power 1 by n is equal to cos 2k pi plus 0 plus I sin 2k pi plus 0 whole to the power 1 by n, and applying the De Moivre's theorem, the power will be come inside here. So cos 2k pi plus 0 by n plus I sin 2k pi by 0 by n. So we can omit this 0 now. So now this complex number have the same modulus 1 and their argument are 0, 2 pi by n, 4 pi by n. In this way we will get the argument for the corresponding value of k. When k is equal to 0, the argument will be 0. When k is equal to 1, argument will be 2 pi by n. Similarly, k is equal to 2. If you put k is equal to 2, the argument will be 4 pi by n. And when you put k is equal to n minus 1, the argument will be 2 pi minus 2 pi by n. Now this complex number cos 2k pi by n plus I sin 2k pi by n is purely real. That means purely real means the imaginary portion is 0 only if this 2k pi by n is an integer. That means if this 2k by n is an integer, means when this 2k by n is an integer, in that case it will be sin integer pi, some integer pi. That means the multiple of pi, the sign of multiple of pi is always 0, so we are left with only the real part. In that case it is purely real. Now we see that what are the possibility that this quantity to be an integer. So we know that the value of the k runs from 0 to n minus 1. So that means 2k by n is an integer only if k is equal to 0 and k is equal to n by 2. There are only two possible value of k for which the quantity 2k by n is an integer. So if n is odd number, then n by 2 is not an integer. So in that case there will be only one real nth root of unity. So that means for n is odd, there is only one real nth root of unity corresponding to k is equal to 0, because in that case n by 2 is not an integer. So that root is 1. And when n is even, there are two real root for k is equal to 0 and k by k is equal to n by 2. The roots, real roots are 1 and minus 1, because cos 2k pi by n plus I sine 2k pi by n. Here if we put k is equal to 0, this sine 0 is 0 and cos 0 is 1, we will get this value 1. And if we put k is equal to n by 2, in that case it will be cos pi, and here this portion will be again 0 and cos pi is minus 1. So these are the two real roots. Now for k is equal to r, we have to put instead of k r, so the root is 2r pi by n plus I sine 2r pi by n. Now for k is equal to n minus r, root is cos 2n pi minus 2 pi by 2r pi by n plus I sine 2n pi minus 2r pi by n. We have to put instead of k r minus 1, we will get this value. Now applying this formula, cos 2 pi minus theta is equal to cos theta. So if we apply this over here, we'll get cos 2 pi 2r pi by n. And next is, if we apply sine 2 pi minus theta is equal to minus sine theta, we will get over here, if we apply this formula, then we will get sine minus sine 2r pi by n. So we see that for k is equal to r, this is the value of the root, and for k is equal to n minus r, this is the value of the root. So we can see these two values are conjugate of each other. Therefore for k is equal to r and k is equal to n minus r, roots are conjugate as well as reciprocal of each other. So we can write the root. When n is odd, the root can be exhibited as 1. 1 is the only real root, and the remaining roots are 2r pi by n plus minus I sine 2r pi by n, where r runs from 0, 1 to n minus 1 by 2. So this plus minus will give the two value of the root. When you put r is equal to 1, 2 up to n minus 1, we'll get two roots. They are conjugate of each other, as we know that the complex root occur in a conjugate pair. Similarly, when n is even, the root can be exhibit as plus minus 1. These are the two real roots when n is even, and the other roots are 2r pi by n plus minus I sine 2r pi by n. So here also roots occur in a conjugate pair. R runs from 0 to n by 2 minus 1. Now let's find the fourth root of 1. That means fourth root of unity. So let z be the fourth root of 1. Z is equal to 1 to the power 1 by 4. So the complex number 1 can be written in the amplitude modulus form in this way: cos 0 plus I sine 0. So z is equal to cos 0 plus I sine 0 whole to the power 1 by 4. So this can also be written as cos 0 can be written as cos 2k pi plus 0, where k is an integer. Similarly, sine 0 can be written as I sine 2k pi plus 0 whole to the power 1 by 4, where this k is an integer. K runs from 0, 1, 2, 3. So k has the 4 value. So applying the De Moivre's theorem, it will be cos 2k pi by 4 plus I sine 2k pi by 4. This 1 by 4 will come inside over here. Again, applying the De Moivre's theorem, I can take this k out in the power of this complex number cos 2 pi by 4 plus I sine 2 pi by 4 whole to the power k, and cos 2 pi by 4 is cos 90, that is 0, and I sine 90 is 1. So we are left with only I to the power k, where k runs from 0 to 3. K is equal to 0, 1, 2, 3. So for k is equal to 0, we will get z is equal to 1. K is equal to 1, we will get z is equal to I. K is equal to 2i square. K is equal to 3i cube. That means I square means minus 1. I cube means minus I. So fourth root of 1 are plus minus 1 and plus minus I. This is for your practice. Find the cube root of the complex number z is equal to 1. Now we are going to find the expansion of cos n theta, sin n theta, tan n theta when n is a positive integer, and theta is real. So by De Moivre's theorem, cos n theta plus I sin n theta can be written as cos theta plus I sin theta whole to the power n. Now I can expand this cos theta plus I sin n theta whole to the power n by binomial expansion. We are going to use the binomial expansion, so it will be cos to the power n theta plus nc1 cos to the power n minus 1 theta I sin theta, nc2 cos to the power n minus 2 theta I square sin square theta, and so on. So this is the binomial expansion. We'll expand like this: a plus b whole to the power n can be expanded like this: nc0 a to the power n b to the power 0 plus nc1 a to the power n minus 1 b to the power 1 plus nc2 a to the power n minus 2 b to the power 2 plus dot dot dot. In this way we'll get ncn a to the power n minus n0 and b to the power n. So if we expand by this formula, nc0 is 1 and ncn is also 1. So here nc0 is 1 cos to the power n theta, and I sin theta whole to the power 0 is 0. So we are left with cos to the power n theta, nc1 cos to the power n minus 1 theta, I sin theta whole to the power 1. So we are getting this term, and so on. The final term will be ncn, that is 1 cos to the power 0, that means 1, and I sin theta whole to the power n, that means I to the power n sin to the power n theta. So now we are going to collect the real and imaginary part separately. So the real part is here cos n theta, and this is also real part because I square is minus 1. This is real part. So alternatively we will get the real part, that means cos n theta minus nc2 cos to the power n minus theta sin square theta, because minus sign because of this I square is minus 1, and after that we'll get plus nc4 cos to the power n minus 4 theta sin to the power 4 theta, because it will be plus because I to the power 4 is 1. Now again we are going to collect the imaginary part. So imaginary part is I over here, so I am writing I nc1 cos to the power n minus 1 theta sin theta, and here nc3 cos to the power n minus theta I cube sin square theta. I cube is minus I, so it will be minus, then so on. We will collect the imaginary part. Now I can equate the real and imaginary part. That means cos n theta is equal to this much here, the real part, and the sin n theta is equal to this portion. So cos n theta, first of all let's see the cos n theta. Here cos n theta is equal to this much. So cos n theta is equal to cos to the power n theta minus nc2 cos to the power n minus 2 theta sin square theta plus nc4 cos to the power n minus 4 sin to the power 4 theta plus dot dot dot, and so on. Now the last term depend on the value of n. So the last term depend on the value of n. When n is even, so last term, that means I to the power even number will be either 1 or minus 1, and it will be not imaginary. So the term will contain, last term will contain sin to the power n theta, and the this sign will depend on the value of it could be minus 1 or plus 1, minus 1 or plus 1. So that is depend on minus 1 to the power n by 2. So the last term will be minus 1 to the power n by 2 sin to the power n theta when n is even. And when n is odd, the last term will be just before the this last term. So minus 1 to the power n minus 1 by 2 n cos theta sine to the power n minus 1 theta. Similarly, when you equate the imaginary part, it will be sine n theta is equal to nc1 cos to the power n minus 1 theta sine theta minus nc2 cos to the power n minus theta n minus 3 theta sine cube theta, and so on. And here also the last term depend on the value of n. When n is even, the last term will be the minus 1 to the power n minus 2 by 2 n cos theta sine to the power n minus 1 theta, and when n is odd, the last term will be minus 1 to the power n minus 1 by 2 n sine n theta. Now we can find the value of tan theta. Tan n theta can be written as sine n theta by cos n theta, and we know that the value of sine n theta is this much and the cos n theta is this much. So we have just derived this series, and dividing numerator and denominator by cos to the power n theta, we'll get nc1 tan theta minus nc2 tan cube theta divided by 1 minus nc2 tan theta plus nc4 tan to the power 4 theta. So this is the expansion of tan theta. Now we are going to find the expansion of cos to the power n theta sine to the power n theta in series of multiple of theta, where n is a positive integer and theta is a real number. So let x is equal to cos theta plus I sine theta, then x to the power n can be written as cos n theta plus I sine n theta. Similarly, x to the power minus n can also be written as cos n theta minus I sine n theta. Now if I add x to the power n plus x to the power minus n, so it will be cos n theta plus cos n theta, that means cos 2n theta, and sine n I sine n theta and minus I sine n theta will get cancelled. Now if I subtract cos to x to the power n minus x to the power minus n, then we will get cos n theta will get cancelled, and we are left with 2I sine n theta. Now if I put n is equal to 1, over here, x plus 1 by x is equal to 2 cos theta, and here also if we put x is equal to n is equal to 1, x minus 1 by x is equal to 2I sine n theta. Now I'm going to take the power n on the both side of this expression, so 2 cos theta whole to the power n, x plus 1 by x whole to the power n. Now I'm going to use the binomial expansion over here. Then this is the first term and this is the last term, their coefficient are same, and this is the second term and this is the second last term, their coefficient are same, nc1 and ncn minus 1, that they are the same value, they have the same value, and so on. So we will get pair. now cos x to the power n plus 1 by x to the power n is equal to 2 cos n theta from here, and similarly x to the power n minus 2 plus 1 by x to the power n minus 2, instead of n we have n minus 2, so here it will be 2 cos n minus 2 theta, and for n minus 4 it will be 2 cos n minus 4 theta, and so on. So this expression containing n plus 1 term, the power is n, so the binomial expansion contain n plus 1 term. If n is even, then total number of term will be odd. There will be one middle term which is free from x, that means that term contain only constant term. And if n be odd, there are two middle term, one containing the coefficient x and other containing the 1 by x. So therefore the last term of the above expression is constant if n is even, and the last term contain cos theta if n is odd. Now similarly we can find the expression for sine to the power n theta. Now let's do one problem. Expand sine to the power 7 theta in terms of the multiple of angle theta. So let x is equal to cos theta plus I sine theta. Then x to the power n minus 1 by x to the power n is 2 sine n theta from the previous result. So x, if I take n is equal to 1, then x minus 1 by x is equal to 2I sine theta. Now taking the power 7 of this expression, so 2I sine whole to the power 7 is equal to x minus 1 by x whole to the power 7. Now if I expand in a binomial expansion, 7c0 x to the power 7, 7c1 x to the power 5. In this way you will expand. First term will be 7c0 x to the power 7 1 by x to the power 0 plus 7c1 x to the power 6 1 by x to the power 1, and so on. So this is the expansion. We have to expand up to 8 terms. Now x to the power 7 and minus 1 by x to the power 7 I am writing over here. 7x to the power 5, 7 1 by x to the power 5 I am combining together, writing together over here, and similarly this term and this term writing together over here, and so on. So 2I sine theta whole to the power 7 can be written as 2I x to the power 7 1 minus x to the power 7. From here I can write 2I sine sine 7 theta. So this can be written as 7 into 2I sine 5 theta. This can be written as 21 into 2I sine 3 theta, and similarly this is 35 into 2I sine theta. So sine to the power 7 theta can be written as, I am taking this term whole to the power 7 over here, it will be minus 1 by 64, 7 sine 7 theta, 7 sine 5 theta, 21 sine 3 theta, minus 35 sine theta. This is your answer. Thank you.